Welcome to the second screencast on queues. We'll be talking about a third implementation of the queue and also another data structure, the double-ended queue or the deck. As we talked about last time, the queue interface extends collection. We have two methods for adding something to the end of the queue or the rear of the queue. We have two methods for looking at the head of the queue without removing. And we have two methods for removing something from the head of the queue, and we know the size of how many items are in the queue. Again, the difference between add and offer is add throws an exception if it's full, offer returns false, element throws the exception, peek returns null, pull returns null, remove throws the exception. So our implementation, our third implementation, is going to be the array-based implementation. We already talked about the linked list implementation, which is the easiest, and the singly linked list implementation, where we actually keep track of our own nodes and size. This implementation is going to be an array-based implementation, so we need to keep track of the front index, where in the array is the front of the queue, where in the array is the rear of the queue, so that's the index of the rear item. The size, because as you'll see shortly, it's pretty complicated to figure out how big the queue is without knowing the size or keeping track of the size. We keep track of the capacity to make it easy on us to know when we're full, because we can say size is equal to capacity. And then we have our data array, which holds the items. So the constructor, for this particular example, I'm going to say the capacity is 8. You can make it 10 or a million, whatever you want. Again, the larger the number it is, you're sort of got empty space in your queue. So don't make it too huge, we'll grow it later. We then create the data array, and again, we have to cast it to type E because you can't construct an array of type E directly. All objects, or everything in Java is a subclass of objects, so we create the object array, cast it to type E. Then we initialize our front, so the first place, or the front of the queue, is going to be at 0. And then we put the rear at capacity -1, so it's at rear. So the rear index right now is actually pointing to the spot before where it needs to be. We'll talk about that again. And then the size. When we create a new a new queue, the size is 0. There's nothing in it. So now let's talk about how we add things to the queue. So the first method we're going to talk about is the add. So if the size is equal to the capacity, so that we have, in this case, 8 items in the queue and our capacity is 8, that means we need to reallocate the array. So I'll talk about that later, about how we do the reallocation, but it's very similar to the stack and the list, where we double the size of the array. In this case, we reorder, or we don't reorder, we copy the items from data into the new array, and then we assign data to this new array after we've copied all the items over. I'll talk about that a bit. Okay, so we're doing an add, so we increment the size, so we say there's one more thing in there. We then update rear, because we add things at the rear. So we say rear +1, and then we have to mod by the capacity to get, so that we do the circular array. And then we assign the data at rear, so we put data at rear is equal to E, so we added E to our queue. And we return true, because in this case we're always going to be successful in our add. If we had a rule that said we have a fixed capacity, instead of reallocating, we can throw a queue fuel, an exception, indicating that we have no room. The offer method, same thing, size is capacity. In this case, we've got plenty of space, so we don't reallocate. We increment the size to 2. We update rear, and this time we don't have to do the mod. Well, we do the mod, but it doesn't have any effect. And then we assign, and so we've now put 2 things into our queue. And so now let's say we want to look at the head of the queue. So in this case, we would throw an exception if we have nothing in the queue. So we check to see the size is 0. That's how we know that we have an empty queue. There's no nodes, so we have to base it upon the size. So if the size is 0, then we throw an exception. Else, we just return the data at front. So we just return the value of data at front. That's the thing at the head of the queue. Now the peek method doesn't throw an exception, it returns null, so we check the size. If it's 0, if it is 0, we return null, else we return the data at front. So we return the thing at the front of the queue. The poll method, again, is the one that doesn't throw an exception, so if size is 0, we return null. Else, now since we're going to remove the thing at front from our queue, we need to remember the value at front. We then increment front and then mod it by the capacity because we're doing a circular array implementation. We got to decrement the size because we've removed something from the queue, and then we return the result. So now front has moved forward 1. In our case, size is 1, so front and rear are the same. So we have removed 1, so the size is only 1. And then if we do the remove, again, if the size is 0, we're going to throw the exception, not return null. Else, we remember the data with a thing at the front. We increment the front. We decrement the size. And we return the result. So this is similar to the initialization case where front was 1 more than rear. It was ahead of rear. So if we were to do an add, we would increment rear and then assign data rear to be the thing, and then the size would be 1. So you can sort of see how if the queue is empty, front will be 1 ahead of rear. But being able to determine the size without remembering it is more math than I can do, so I keep track of the size to make it simple. So what does the reallocate method do? We need to double the size of the array. So we create a new capacity, we double the size of the old array, we create a new array, new data to hold the new stuff. We assign a variable to front because we're, instead of having it possibly bound over the circular array, why don't we just put it from 0 to size in the new array? We can move things to so it's nicer. Because we now have a larger array, we know that we will not fill up the array when size, because size was capacity, and so the array is now twice as big. So we just do a loop to copy the data from the old data array into our new data array. We make sure we do the incrementing of j based upon the capacity, because that's the old value. So if it was circular, we'll get the right value into new data. We then assign front to be 0. We're starting at 0, right? Because we just moved everything into 0. Rear is size minus 1, because that's the last thing, that's the last index of our array. And the capacity is the new capacity, and then we overwrite the data with the new data. So we now have all the things in the new data, and it goes from 0 to wherever. So that's our new array. So we now have a new array. We've got plenty of space. We can continue on our merry way. I want to talk about the iterator for an array. So we have a private class inside. Didn't talk about it about the previous screencast. We could do the same thing with the linked list implementation. We would just defer to the linked list iterator. Also, for our own singly linked thing, we would keep a pointer to front and then just keep going on until we get to rear. But with the linked list, or excuse me, the array implementation, our iterator, we keep track of the index, so where we are in the array, and we keep track of how many elements we have returned on our next call. So we know when we're done. So our constructor says we want to start at front, right? Because we start at front and we go to rear. And so now the has next to say, well, the count is less than size, so we haven't visited all the things in the queue. And then the next is simply, we check to see if there's nothing next, then I throw a no such element exception. And there's a typo in my slide, I need another parenthesis in the if statement. Else, so we have a next, we get the data at index, we do our increment of index, and we do the mod capacity, so we're going to do the circular array thing so that we know go back to the beginning. We increment count, and then we return count. So each time we call next, we'll make sure that there's room in there, and then we will move along, increment our count. So once the count is equal to size, has next will be false, or has next will be false, and then we'll throw the exception. So the second data structure that we want to talk about that's similar to a queue is a double-ended queue, where you can add to both ends of the queue. So you can insert and remove from both ends. You can insert from the front, you can remove from the rear. So we had to add new names, so it's offer first, offer last, add first, add last, poll first, poll last, peak first, peak last, remove first, remove last, and still has a size. There's nothing special about size. You have two iterators on the deck. You can go from the front to the rear, or you can go from the rear to the front, because you can consider it as being a doubly ended queue. So you can go from the front to the rear, or you can go from the rear to the front. As a queue, you could use a deck as a queue. Just do adding at the front, or remove from the front and add to the rear. You just do half of it. But you can also use a deck as a stack, where you pick one end. So let's say I want to do a push. That's the same as doing add first, and then I do pop, which is remove first, and peak is just peak first. So I could use a deck as a queue as the implementation of, I can use a deck as an implementation of a stack, as long as I use the right thing. And then the empty method is just asking the question, is the queue or is the deck empty, or is the size equal to 0? So they're very useful data structures. They're often wrapped in an implementation so that you don't have all the, you can use a deck as a stack or as a queue. You just have to not use the other methods on the deck. I prefer doing it where I would use a stack class, or I would implement a stack class to remove all the extra methods that might get a little confusing, that if you see, oh, I've got a deck so I can add to the rear, well, that just blew away your stack. So you can do it, it's very useful, it's a very powerful thing. Or you could just use the queue, or you could use the stack, or you could even use a list as a queue, just not doing things, or not removing from the middle, etc. Got to remember that these data structures are here for a reason, and the interfaces allow you to focus on the purpose of the data structure. So the queue is, you add at the rear, you remove from the front. Deck, you can add and remove in both ends, but you can't get to the middle on either of these data structures. Thank you very much.